Hello students, what's up? I hope you all are fine. So today we will discuss the second lecture of this amazing chapter, magnetic effect of electric current. So let's start this class without any delay. So let's move on to the next slide. Here we are. So in this slide, we will study about the magnetic field lines due to a current through a circular loop. So basically, yet we have seen the magnetic field lines in a straight conductor. Okay, straight current carrying conductor. So how can we find out the direction of magnetic field lines in this condition? We can simply apply the right hand thumb rule. Applying right hand thumb rule. Right hand thumb rule. But in this case, we have to find out the direction of magnetic field lines in a circular loop. This is a circular loop. Okay, and this is a battery. Current is going in this direction from this direction, and it is moving like this, and it is going out from this direction. Okay, guys. So basically, to find out the direction of magnetic field lines, in this case, what do we have to do? We have to cut it in some parts. Okay, let's suppose break it in some parts. Now this is a part first, and let me find out the direction in this part. So let's take it out here. Okay, now guys, you can see then this part is appearing like a straight conductor. Okay, and current is going in this direction. So we can find out the direction of magnetic fields in this straight conductor because we know the right hand thumb rule. We can apply this right hand thumb rule here simply, and we will get the direction of magnetic field lines. Okay, guys. So let me apply the right hand thumb rule here. So to applying this rule, you have to keep your thumb in the direction of current. You have to keep your thumb straight, and you also have to keep it in the direction of current. So your curved finger will be showing the direction of magnetic field lines, the direction of magnetic what field lines. Okay, guys. So now we have to find out the magnetic field lines on this part also. Okay, for on this part. So here the current is moving upwards. Now when you apply the right hand thumb rule, then you will find out that the magnetic field lines is like this. It is entering for our side and it is going out from the another side. So basically, this is the direction of magnetic field lines in this case. Now, let's find out the direction of magnetic field lines of this part. Let's suppose this part. So let me take it out, and it will be appearing like a straight conductor, but you can see that current here is going downside. In this condition, current was moving upside, but here it is going down. Okay, because this is current and it is going in, it is flowing in this circular loop, and here the direction is like this, and here the direction will be like this. So basically, guys, what happens here, you have to apply the right hand thumb rule. And when you apply the right hand thumb rule, then you will find out then the direction of the magnetic field lines will be like this. Okay, will be like this. It is entering from our side and going out from the opposite side. So guys, what we have observed here, we have observed then in the center, you can see in the center, the magnetic field lines are entering. Okay, when we see it by this side, then you can see that magnetic field lines are entering. So if you observe from the other side, then magnetic field lines will be appearing to be going out from the other side. So if I compare this circular loop with a bar magnet, so let me draw a bar magnet for you. You can see this is your bar magnet. This is your north pole. This is your south pole. So what happens? The magnetic field lines goes out of the north pole like this. Okay. And it appears to be coming in south pole like this. This is your south pole and magnetic field lines are coming in south pole. Okay, so here in this part, these lines are coming, so this will be acting as a south pole. Okay, let me write down here for you. South pole, and the opposite side will be acting as a north pole. Okay, the opposite side will be acting as a north pole, because from that side these magnetic field lines are what? They are going out. Okay, but this south pole, why we are saying this south pole? Because magnetic field lines are coming from it. Okay, so this is the case of circular loop. I hope guys you understand this. Now let's move on to the next slide. Okay guys, so here we are. Here we will see, in case of a circular current carrying conductor, the magnetic field lines will be in the form of iron concentric circles around every part of the periphery of the conductor. That you can see that in each part you will see magnetic field lines. And why we are seeing this magnetic field lines? Like, how did we find out the direction of these magnetic field lines? By the right hand thumb rule. By the right hand thumb rule. Okay guys, so the magnetic field will be stronger near the periphery of the loop. Here near the periphery, the magnetic field will be stronger. Why? Because you can see that here the closeness of the magnetic field line is higher, but as soon as they are going far away, the closeness is increasing. Or you can say that they are going at a distance. The distance is increasing. So that's why the magnetic field will be decreased. Okay. On the other hand, the magnetic field lines will be distant from each other when we move towards the center of the current carrying loop. So as soon as you go towards the center, then these magnetic field lines will be going far. Finally, at the center of the arcs, big circles would appear as a straight line. Here it is written that the big circles would appear as a straight line. As a straight line. Okay guys, you can see that here this is curved line, this is curved line, but as soon as these length increase, then they will be appearing like a straight line. Okay, so I hope guys you understand the magnetic field lines by a circular loop. Now let's move on to the next slide. Okay, here we will discuss clock face rule. So basically, a current carrying loop works like a disk magnet. The polarity of this magnet can be easily understood with the help of clock face rule. If the current is flowing in anti-clockwise direction, then the face of the loop shows north pole. On the other hand, if the current is flowing in the clockwise direction, then the face of the loop shows south pole. So basically, let me cut it short for you. The language is a little bit difficult. Basically, according to this rule, by this clock face rule, we can simply find out the polarity of a circular loop. Let's suppose this is a circular loop and current is flowing in this direction. Okay, so you have to remember that according to this rule, if the current is in anti-clockwise direction, then this phase will make north pole. And if the current is in clockwise direction, sorry, let me erase it from here. Clockwise direction, then it will be making south pole. Okay, so you can see, let's suppose this is direction of current, this is a circular loop, so this is the direction of current. And now let me tell you and let me ask you basically that current here is anti-clockwise or clockwise. This is a question for you. Is it anti-clockwise or clockwise? Because I told this thing in the previous lecture, that how to find out anti-clockwise direction or the clockwise direction, and I had also told you the trick. Okay, so I hope guys you all know the answer. So let me tell you the answer. Basically, this is anti-clockwise direction. This is not clockwise, this is anti-clockwise direction. Why? Because let me tell you, let's suppose making an N, and this is the direction of the current, this is also the direction of the current. So here it is appearing like N, so this is anti-clockwise direction. And if the direction is anti-clockwise, so which type of pole will it be? It will be north pole. It will be north pole, because we know this by this clock face rule. This clock face rule tells us that if the direction of current is in anti-clockwise, then the pole will be acting as north pole, and if the direction of current is in clockwise, then the pole will be acting as south pole. Okay guys, I hope you understand this point. Now let's move ahead to the next slide. Okay, so here we have to talk about some little information about this strength of the magnetic field. Okay, so basically guys, the strength of a magnetic field line at the center of the loop depends on these, some points. So the strength of magnetic field, not magnetic field lines, the strength of magnetic field. So this is the first thing on which the strength of a magnetic field depends. So the first thing is radius of the coil. So the strength of the magnetic field is inversely proportional to the radius of the coil. If the radius increases, the magnetic strength at the center decreases. So let's suppose this is your circular loop and this is your current going like this. Okay. Okay, guys. So let's suppose the radius of this circle is R. Okay. Now let's take another circle, and this time we have taken a big circle. So in this case, let's suppose the radius is R1 and this R1 is greater than R. So what happens in this second case, the magnetic field will not be as stronger as in the first case. Why? Because radius here is higher. You can see the distance here, the distance of the center is higher. This is your center here, this is your center. So distance from the center is higher in this case. So that's the reason that the magnetic field will not be as stronger here as in this case. I hope you get my point. Now let's talk about the second term, the number of turns in the coil. Let's talk about the number of turns in the coil. So as the number of turns in the coil increase, the magnetic strength at the center increases. Okay, let's suppose if in the place of single turn, let me take 2 turns like this. Now, if you in this case, if you find out the strength at the center, then this will be higher than the single turn. Okay, it will be higher than the single turn because the current in each circular turn is having the same direction, thus the field due to each turn adds up. Because the current is also flowing in this direction, it is also flowing in this direction, so they both have their magnetic field, and at the center the magnetic field will be added up. Okay, so that's why if you compare it with a single turn, then in this case the magnetic field strength will be higher. I hope you understand this. Now let's move on to the next slide. Okay guys, so here we will have to find out the strength of a current flowing in the coil. As the strength of the current increases, basically what happens when the current increases, let's suppose this is again your circular loop and here the current is increased. This is, let's suppose this is case number first, and let's take case number second. This is also a circular loop and current is flowing, current also flowing here. This is I1, and if this I1 is greater than I, then the magnetic field at the center will be higher in comparison of this first case. Okay, in this case, let's suppose this is case number second. So here the current will be higher. Why? Because, sorry, here the magnetic strength will be higher. Why? Because the current is higher. So you can say that magnetic field also depends on the magnitude of current. Magnetic field strength. I hope guys you know already what is the meaning of this magnetic field strength. Let me tell you how much a magnet feels, or you can say experience a force is shows by the magnetic field strength. If magnetic field strength is higher, then the magnet will be experiencing more force. But if the magnetic field is, or you can say the magnetic field strength is lesser, then it will experience lesser force. So I hope you get this point. Now guys, magnetic field strength is proportional to the current. You can say is proportional to the magnitude of current. Okay. Now let's move ahead. Let's talk about the fourth case. So the fourth case says that magnetic field due to a current in solenoid. Okay, so first of all, let me tell you what is a solenoid. So solenoid is nothing if you added a single turn. Okay, because we know, let's suppose this is your circular loop, and when we know that how can we calculate and how can we find out the direction of magnetic field in this case. Now if you keep adding these turns like this, then it will simply become a solenoid. So this will be looking like this. This is one turn, this is another turn, this is third turn, and if you keep turning it, then it will become a solenoid. So basically, let me tell you the direction of the magnetic field lines in a solenoid. So we know that in a single turn, if the current is in anti-clockwise, sorry, clockwise, then those, or you can say that side of the circular loop will be acting as south. So here in this case, you can see that these magnetic field lines are entering in this solenoid. So this side will be acting as south pole. Okay. Now from this side, it is going out. The magnetic field lines are going out. So this will be acting as north pole. This is what? North pole. Okay. So this is the direction of current, and we already know, because in the previous slide I told you that how can we find out the direction of the magnetic field lines if we know the direction of the direction of electric current. So I hope guys you understand this solenoid. Now let's read this theory. Solenoid is the coil with many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. A current carrying solenoid produces similar pattern of magnetic field as a bar magnet. So I hope you understand the meaning of this line. We are comparing it with a bar magnet. You can see that this is a bar magnet, and in bar magnet what happens, magnetic field lines goes out from the north pole like this, and it enters in the south pole like this. Okay, it enters in the south pole, so that's why it is acting as a bar magnet. One end of a solenoid behaves as a north pole and another end behaves as the south poles. Now guys, let's move ahead. Okay, so here we will see the pattern of magnetic field lines. So basically guys, magnetic field lines are parallel inside the solenoid. So if you see inside the solenoid, then you can observe that magnetic field lines are parallel, because in the case of circular loop, what happens if you make its magnetic field lines, then in the center it will be appearing, the magnetic field lines will be appearing parallel. So you, in solenoid, what we have done, we have simply adds up lots of turns. So that's why guys, what happens, in the center of a solenoid, the magnetic field lines will be appearing as a straight line. So magnetic field lines are parallel inside the solenoid. It will be parallel inside the solenoid. Similar to a bar magnet, it will be similar to a bar magnet. You can also compare it with this diagram. This is the diagram of a solenoid, and this is the diagram of a magnetic field lines in a bar magnet. So you can see that inside the, the magnetic field lines are parallel. Magnetic field produced by a solenoid is similar to a bar magnet. The strength of magnetic field is proportional to the number of turns and magnitude of current. So simply, if the number of turns are higher, then what will happen? Their magnetic field will be added up. Okay, so that's why the strength of magnetic field will also be higher. Okay, if the number of turn is higher. Now if you increase the current, then we know that current is proportional to the magnetic field strength. Magnetic field strength. So in this case also, the current will be higher, so the magnetic field strength will also be higher. By producing a strong magnetic field inside the solenoid, magnetic materials can be magnetized. Magnet formed by producing magnetic field inside a solenoid is called electromagnet. Basically guys, what do we do? What is the use of this solenoid? We actually enter a material inside it. Let's suppose, let me take some material. Okay, so what happens if you keep a material inside it, and if you make it, if you provide current from it, then the magnetic field lines will be entering, or we can say that a magnetic field will be generated inside it, and the material which is kept inside it will also be magnetized. Let's suppose I had kept some material inside it, so this material will also be magnetized. Okay, so now guys, magnet formed by producing magnetic field inside a solenoid. So this type of magnetized material are known as electromagnet. So I hope you understand this point. Let's move ahead. Now guys, let's talk about an electromagnet. This is very, very important. What is an electromagnet? So an electromagnet consists of a long coil of insulated copper wire wrapped on a soft iron. So an electromagnet consists of a long coil of insulated copper wire wrapped on a soft iron. So basically, this is a solenoid. Okay, and these are the copper wires, and these copper wires are insulated. Now you can question that why it is insulated, because we have to keep a material inside it. If these are not insulated and if we directly connect it with a material, then this will be short circuit, because it will be directly in touch of this copper wire. So the current will start to flow across this material as well. So we just want the magnetic field to be in contact with this material. We don't want current to be in contact with this material. So that's why we insulate it. So guys, what happens when you keep a material inside it and when you provide current, then this solenoid will become, or you can say this will become an electromagnet. Okay, but this will be acting as electromagnet until you provide, the current inside it. If you stop providing current, then it will also stop behaving as an magnet. So I hope guys you understand what is a electromagnet. Let's move on to the next slide. So here on this slide, we will study about a force on a current carrying conductor. This is very important, a force on a current carrying conductor. So first of all, let me draw a diagram for your understanding. Let's suppose this is a magnet. This is its north pole and this is its south pole. So the magnetic field lines will be like this. They are at equal distance. They will be like this, and they are also at equal distance. Okay, so if these are in equal distance, this simply means that magnetic field is same. Magnetic field is same. Okay, why it is same? Because we know that if the closeness, if magnetic field lines are closer to each other, let's suppose this is a magnet, this is a bar magnet, this is its north pole. So here near the poles, the magnetic field is high. The magnetic field is higher. Why? Because here you can see that magnetic field lines are closer, but here the magnetic field is lesser. And why it is lesser? Because the magnetic field lines are at distance here. Okay, but here the distance is same. So that's why magnetic field will also be uniform. Okay, we will call it uniform magnetic field. So guys, what happens when you keep a conductor here? Okay, let's suppose this is a conductor. So this is made up of copper. So now let me ask a question from you. Then will it experience a force or not? So I hope guys you all know that if you are not providing current inside it, then it will not be experiencing any type of force, because it is not a magnet. Magnet always attracts magnet. It is copper is not a magnet, so it will not be attracting or repelling in this magnetic field. So guys, if I provide current inside it, if I flow current inside it, then definitely it will exert force on this conductor. Why? Because you know that current has also its magnetic field. Okay, it will start acting like a magnet. So this magnet will exert a force on this current carrying conductor. So now we have to find out the direction of that force. It is very, very important, and the questions are also asked on the basis of this concept. So first of all, let me read the theory. Force on a current carrying conductor in a magnetic field lines we are studying. So a current carrying conductor exerts a force when a magnet is placed in its vicinity. Similarly, a magnet also exerts equal and opposite force on the current carrying conductor. This was suggested by Marie Ampere, a French physicist and considered as founder of science of electromagnetism. So basically, this is not a big deal. Here it is written that this current carrying conductor will experience a force, and this was given by the Marie Ampere, which was a physicist, and we can also say him science of electromagnetism. We can also say him the founder of science of electromagnetism. Now, the direction of the force over the conductor gets reversed with the change in direction of flow of electric current. It is observed that the magnitude of force is highest when the direction of current is at right angles to the magnetic field. So here let me tell you what is written. Let's suppose this is your current carrying conductor. Okay. So now what will happen? This conductor will experience a force. Now, if you keep this conductor in this direction horizontally, then it will not experience any type of force. If you keep it here like this, then it will start to be experiencing a force. And when you keep it at 90 degree from this magnetic field, this is, let's suppose, angle of 90 degree. So the force exerting on it will be highest at this point. When it is making right angle, the force being exerted on it will be highest. So these things are the observations, but we do not need to understand all these observations. This is just an, you can say, extra information. The main aim of this topic is we have to find out the direction of the force. It is very, very important. So to find out the direction of the force, let me take you to the next slide. Okay, so here we are. So here the Fleming's left hand rule comes. It is very, very important rule to find out the direction of the force on a current carrying conductor in a magnetic field. So what can we do? Basically, we have to use our left hand. Okay. So in this picture, you can see this is your left hand. Now, what do you have to do? You have to keep your thumb, your index finger, okay, and your middle finger perpendicular to each other. They should be mutually perpendicular to each other. Now, if you keep your index finger in the direction of magnetic field, and if you keep your middle finger in the direction of current, then your thumb will be showing the direction of motion, or you can say thrust. Okay, or it simply means it is talking about force. Okay, so your thumb will be showing the direction of the exerted force. Now I hope, guys, I think you might not be able to understand it. So let me give you an example. Let's suppose this is your magnet. This is the north pole of the magnet, and this is the south pole of the magnet, and this is a magnetic field lines like this. Okay, and this is your current carrying conductor. Now guys, what do you have to do? First of all, you have to keep your middle finger in the direction of current of your left hand. You have to remember this fact, because in exam students get confused. We are talking about, this is left hand rule, so you have to apply this rule by left hand only. So guys, what do you have to do? You have to keep your finger, okay, in the direction of current. You have to keep your middle finger in the direction of current. So this is the direction of current. Keep your middle finger here, and your index finger should be showing direction of magnetic field. So this is the direction of magnetic field. Okay, I hope guys you understand this point. First of all, understand this step by step, otherwise you will get confused. First of all, first step is you have to keep your thumb and index finger and middle finger perpendicular to each other, like this, like in this picture. Okay, and you have to keep your index finger in the direction of magnetic field. Keep your keep your middle finger in the direction of current, like this. Okay, now your thumb will be showing the direction of force. So what is the direction of force? If you apply this rule here, then the direction of the force will be inside it. Okay, you can say inside this page, and for inside this page we use this cross sign. Okay, this cross meaning inside this page, and this dot meaning outside the page. So the current will be inside the page. Okay guys, sorry, the force exerted will be inside the page. I hope you understand this point. So this is how we find out the direction of the force by applying this Fleming's left hand rule. And when we see some questions on it, then definitely we will be master to find out the direction, in finding out the direction of the force. Now here is some theory. The same thing is written, that if the direction of electric current is perpendicular to the magnetic field, then the direction of force is also perpendicular to both of them. The Fleming's left hand rule states that if the left hand is stretched in a way that the index finger, the middle finger, and the thumb are in mutually perpendicular directions, then the index finger and middle finger of a stretched left hand show the direction of magnetic field and direction of electric current respectively, and the thumb shows the direction of force acting on the conductor. So this is important point, that our thumb shows the direction of force acting on the conductor. The direction of electric current, magnetic field, and force are similar to three mutually perpendicular axes, x, y, and z axis. Many devices such as electric motor, electric generator, loudspeaker work on Fleming's left hand rule. So basically this thing we also had discussed when we started the lecture, that this magnetic field is used in electric generators, electric motors. We will definitely discuss these appliances later in this chapter, but you have to remember, then we calculate or we find out the direction of magnetic field lines by this Fleming's left hand rule. I hope guys you understand this. Now let's move on to the next slide, and let's talk about some questions. Okay, so these questions are very important. Let's try to find out the answers of these questions. So basically the first question here is, why cannot two magnetic field lines intersect each other? Okay, so basically let's suppose to answer this question, I'm writing solution here. Let's suppose this is a magnetic field line and this is another magnetic field line. We know that it doesn't intersect, but to answer this question we have to assume, we have to assume this is called contradiction method. Okay, so we have to assume that they are intersecting each other. Now what will happen in this case guys, this magnetic field lines have two directions. If at this point they have two direction, in this direction as well as in this direction. So because a magnetic field lines cannot have two direction, so that's why they cannot intersect each other. So what would I write? Because magnetic field lines cannot intersect each other, sorry, Let me erase it. Cannot have two directions, so that's why they cannot intersect each other. Okay guys, I hope you got this point. Now let's talk about the second question. Find out the direction of magnetic field lines in a straight conductor when current is passed from up to down. So it is very simple. Let me write the solution. So let's suppose this is your conductor, and here it is said that a current is passed from up to down. The current is passed like this. Okay. So if you apply the right hand thumb rule, then you can find out that in this case, the direction of magnetic field will be like this, in this direction. Okay. Because we have to keep our thumb in the direction of current, and our fingers will be showing the direction of magnetic field. So it is the direction, and this is clockwise direction. Clockwise direction. So I hope guys you get this point. I hope you understand whatever we learned here. So thank you so much. See you later lectures. Bye bye.